Good afternoon, everyone. Welcome to this third talk in the series of Reality of Net Zero. My name is Nick Eyre. I'm Emeritus Professor of Energy and Climate Policy in the Environmental Change Institute at the University of Oxford, and I was a founding co-director of the Zero Institute in the university. I'm going to be your speaker today. But I want to acknowledge the input from my Zero Institute colleague Radhika Khosla on issues to do with equity and international distribution. So the subject of the talk today is zero carbon energy systems, subtitled The Heavy Lifting for Net Zero, and I hope in the next half an hour or so to show you why that subtitle is there. So the content of what I'm going to be talking about is a quick introduction to the link between energy and climate change, which I suspect will be very familiar to most of you. Then talk about decarbonising energy supply, the importance of thinking systemically when we're looking at decarbonising the whole energy system, and then why energy efficiency is an important part of the net zero agenda. And I'll end, if there's time, by talking about some of the remaining challenges that need to be addressed to get us to zero carbon energy systems. So let's start with energy and climate change. This diagram is a bit complicated. Apologies for that. It's from the IPCC technical summary, the most recent one. If you look at the left-hand side diagram, it shows you where we need to get to balance emissions and removals. That, of course, is what we need to do to get to net zero. In principle, any combination of removals and emissions reductions will do, but all the analysis shows that the cost of removals means that most of what we need to do is emissions reduction. 80% at least, probably nearer 90% in the more realistic scenarios. And that's why we say that emissions reduction is doing the heavy lifting of net zero on its own. It's not sufficient, but it needs to do an awful lot. So emissions reductions, in essence, implies very large reductions in fossil fuels. This diagram, also taken from the IPCC, explains why. This is what global greenhouse gas emissions have been doing over the last 30 years. And you can see that CO2 emissions in particular are dominated by emissions from burning fossil fuels. Something like 80% of CO2 emissions are from fossil fuels. That's 64% of all greenhouse gas emissions. So it's very clear we need to reduce fossil fuel emissions very significantly. And of course, fossil fuels are the central part of current energy systems in most countries. So this diagram, taken from the Statistical Review of World Energy, shows you where our energy comes from globally, dominated by oil, the light blue, natural gas, the orange, and coal, the black, between them contributing more than 80% of world energy supplies at the moment. So it's clear that we're looking at a huge change in the global energy system if we're going to decarbonize, the energy system. And that's not the only change we need in the energy system. It's important to remember that the energy system isn't there just to be decarbonised. It's there to provide us with energy. And energy use globally is currently highly unequal. This diagram, again, taken using data from the Statistical Review of World Energy and from our friends in Our World in Data, shows that per capita energy use exceeds 100,000 kilowatt hours per year in a few countries in the Gulf, for example. It exceeds 30,000 kilowatt hours a year in much of the developed world. And yet in parts of sub-Saharan Africa, per capita energy use is still below 1,000 kilowatt hours a year. And the reason for that, of course, is that many people in those countries don't have access to modern energy. So it's important when we're thinking about decarbonising global energy supplies to remember that very large numbers of people still don't have access to modern energy, despite universal access being a sustainable development goal by 2030. In practice, progress is being made towards that, but not quick enough to reach that target at current rates. And the latest data we have is that more than 685 million people had no access to electricity, and over 2 billion people had no access to clean fuels for cooking. So there's a huge challenge in getting clean energy to people, as well as in decarbonising the energy that we've got in the developed world. So the global energy challenge is relatively easy to state. We need huge reductions in fossil fuel emissions to stabilise the climate. Fossil fuels dominate current energy systems, and energy systems underpin modern life and development in countries where development is needed. So the combined challenge is very large. It's clear that just stopping producing fossil fuels is not a viable solution, despite people who claim that it is. We actually need a better energy system. We need one that's based on decarbonised energy supply and actually on improved energy efficiency as well. And that's what I'm going to be talking about for the rest of the talk today. So, decarbonising energy supply. What are the options? Well, three, really. Renewable energy sources, continuing to use fossil fuels, but applying carbon capture and storage, normally called CCS, and nuclear power. Again, in principle, any combination will do. But in practice, renewable energy sources now are way out the leaders in terms of the economics and the investment going into them. So I'm going to focus today on renewable energy sources. Happy to answer questions on the others, but I hope to show you that renewables are very likely to be the dominant supply options in future. Let's dispense with one fiction that some people continue to promote, which is that renewable energy can't supply the whole of global energy. This is a diagram taken from an older IPCC report, but it's still valid because it's about the renewable energy resource. So wind energy alone can supply an order of magnitude more than current electricity use. Solar energy can supply the whole of global energy use between 10 and 100 times over. Even in the most densely populated countries in the world, such as the UK, there is easily sufficient renewable energy around to provide 100% of our energy. There is no real doubt about that. That's not the issue. The issue is capturing it and using it. So at the moment, as I said earlier, renewable energy is a relatively small fraction of global supply. This shows how supply has changed from 1990 out to the current day. And you can see there wind and solar contributing a relatively small amount in recent years. I've been giving talks like this for a number of years. In 2010, those shares were scarcely visible. So progress is being made, but we shouldn't overstate how much renewables are currently contributing to global energy supply. If we look at electricity supply, just the energy that's used to make electricity rather than total energy supply, then wind and solar are clearly playing a much larger role, still small compared to some of the other fuels, but larger. And most impressively of all, I think this curve is really important. It's showing that share of supply is changing at a very rapid rate, and that's because most of the investment in electricity supply is now going into renewables. So again, caution that the top end of that of the y-axis there, 4,500 terawatt hours a year. Total electricity supply is about 30,000, but you can see that the direction of travel, if continued, indicates that renewables are going to play a very major role within the next decade or so. It's a huge transition, not one that people envisaged certainly 20 years ago, but already happening at pace. Why is that happening? So the growth in renewable supply is linked to declining costs. So these are the two diagrams here. On the right-hand side, these are the numbers just for solar, the growth in solar supply, and you can see huge changes over a relatively small number of years as investment goes into solar. On the left-hand side, what's now, I think, quite a famous curve for many of us who work in energy, the decline in costs in solar energy. And I just must flag that the y-axis there is a logarithmic scale. What we've seen since 1976 is a fall in costs of more than a factor of 100. If you'd wanted to buy a 2 kilowatt solar panel in 1976, it would have cost you £300,000. The wholesale price now is nearer £1,000. So a huge change. And the important point to make is that these two diagrams are intrinsically linked. You can't really put a direction of causality on the relationship between them. Falling costs drive the uptake of solar, an increase in solar energy use and the production of solar panels drives the reduction of costs. You've got a positive feedback loop that's leading to system disruption. So wind and solar are now the lowest costs of electricity almost everywhere, which is why they are now the main areas of investment, and I think will continue to be the main areas of investment, even in countries where there's political opposition to them. And it means that other zero carbon options, nuclear power, fossil fuels with CCS, are uncompetitive almost everywhere, uncompetitive with solar and wind. So we're seeing a systemic change in the global electricity system, which should lead to its rapid decarbonisation. So just to summarise where I think the argument is with decarbonising energy supply, the current contribution of renewables is small, but it's growing rapidly. Solar and wind now out-competing conventional sources of electricity as well as other low-carbon sources of electricity and dominating investment. So future electricity will be very largely from renewables, i.e. the sustainable flows of energy from the natural environment, a truly sustainable energy source. So this is great, isn't it? Doesn't this mean we've cracked the problem that in 10 years' time we'll all be able to sit back and say we've got a zero carbon energy system? Sadly not, because those conclusions there are largely about electricity, but electricity is only a small part of energy use. And we need to think about how to decarbonise the other ways that we use energy, the ways we use fossil fuels directly in industry, in buildings, and in transport. And that will be the harder part of the decarbonisation story. That's why I think we need to think systemically about energy. We need to think across the whole spectrum of the ways that energy is used. So if we think about the whole energy system, it's complicated. There's no way of avoiding that conclusion. And the next 4 slides are all going to look a bit like this. They're my attempt to simplify the issue as much as I can. So essentially, energy flows from the left-hand side of the diagram to the right-hand side. The energy system incorporates the sources of energy, the energy conversion system, and the services provided by energy, the uses that we make of energy. So you've got fossil fuels, wind, solar on the left, for example, and you've got heating, lighting, transportation on the right. And the other distinction this diagram makes is between heat and work, both of which are forms of energy. So heat is the internal energy that matter has because essentially of the vibrations of atoms within it. And work are all the other sources of energy. So typically you might think of mechanical energy and electrical energy. And all the conversion system does is take you between the energy sources and the energy services. On the left-hand side there, you've got some energy sources, fossil fuels, nuclear, biomass, geothermal that produce heat, and others that produce work, typically electricity, so hydropower, wind, solar PV, the main sources of renewables as it happens. And on the right-hand side, the different uses of energy, some heat for heating, washing, cooking, etc., and some work, stationary power, transportation, cooling, lighting, electronics. So that's what a generalized energy system looks like. Hundreds of years ago, it was all very simple. This is what the same diagram in a pre-industrial society looks like. In practice, there wasn't really an energy system as such. There were two separate systems, one for heat, one for work. If you wanted to use heat, you burnt something, normally wood. If you could find some fossil fuels, great, but normally people were burning wood to provide those heating energy services. If you wanted work for stationary power to mill your grain, for example, or transportation, then if you were lucky, you lived near a small watermill or windmill, but normally you would be using the power of some animal, a strong animal, if you could afford one and pay and use it. Otherwise, people's own power, people's own energy. That's why it's called work, because people had to do some physical work to get these services. The Industrial Revolution changed all that, and it did so because we learned how to transform. Firstly, we learned how to mine fossil fuels in large amounts, and then how to transform it, not just into uses of heat, but to uses of work as well. So steam engines, internal combustion engines, steam turbines, gas turbines, all of which allow that diagonal large arrow using heat to provide work. And in doing that, fossil fuels really largely displaced the traditional sources of work, so that all our energy, or almost all our energy, came from fossil fuels, with some nuclear, some hydropower, but very largely fossil fuels, as I showed you earlier. And that uses boilers and furnaces to provide things like heating and cooking. But then the ways of transforming heat into work, largely through internal combustion engines and turbines for electricity now. So that system is great at providing us with energy, but of course it's terrible for climate change because it relies so much on fossil fuels there to provide the bulk of our energy. What does a future energy system dependent largely on renewables look like? Well, radically different is the answer. It's not just a case of plugging in one sort of fuel instead of another, because it changes the whole energy conversion system. So if our principal sources of energy are wind and solar, they're sources of work. Through electricity, they provide stationary power transportation. But if we want to provide heat, then we have to somehow change the electricity into heat. That can be through simple resistive heating. It can be through heat pumps. It can be through making hydrogen to burn if you actually need fuels. And that's why that diagonal arrow in the other direction in this diagram, the last diagram, you'll remember a diagonal arrow, top left to bottom right. Here, the interesting arrow is bottom left to top right. turning work into heat. So as I said, a very radically different energy system in future, which is why we need to think about the system as a whole. If we can do that, what are the impacts on energy use? What practically might energy use look like in the future? So this is a diagram taken from a piece of work I did about 5 years ago now. The diagram shows on the left the current energy system, energy use split between industry, buildings and transport, and the same on the right-hand side, but in a post-energy transition world. And in both cases, I've split the uses of energy between fuels and electricity. So on the left there, fossil fuels and electricity, that's pretty much what the current energy system looks like. Very much dominated by the direct use of fossil fuels, but with significant use of electricity in industry and buildings. If we move to a post-transition system, and I've made some assumptions just to aid the calculations here, no improvements in energy efficiency, no increases in the demand for energy services, not realistic assumptions, but just to identify what the changes result from the transition. And the thing you can immediately see is a much increased use of electricity. So particularly in buildings and transportation, electricity taking a much larger share. Still some use of fuels, coloured differently because the fuels won't be fossil fuels in this case. They'll probably be hydrogen or some other fuel made out of hydrogen, which is itself made out of electricity. So electricity's share rises very significantly from something like 26% of global energy use to 77%. But the other thing that you can see is that overall energy demand falls, and that's in essence because we can use electricity more efficiently than we can use fossil fuels, and that makes a huge contribution to the overall energy transition. In essence, this happens because there's a synergy between renewables, electrification, and efficiency. And if there's one thing I'd like people to take away from this talk, it is that the energy transition is in essence about renewables, electrification, and efficiency and the way that they work together. If you want to understand that, then you need to know a little bit about the second law of thermodynamics. I do find when giving this talk that any mention of laws of thermodynamics divides the audience into two. So for those of you who are physical scientists, please just look at the diagrams and the equations on the right-hand side. They'll convince you that I know what I'm talking about, hopefully. For those of you who slightly balk at the laws of thermodynamics, don't panic. All you really need to know is that work can be converted into heat more efficiently than heat can be converted into work. That is the upshot of the second law of thermodynamics. And it is absolutely crucial when thinking about the energy transition, because as I've just been trying to show you, we are moving from a system dominated by heat supply to one dominated by work supply, and that's why the future system can be much more efficient. If you want to think about it more concretely, think about what each unit of renewable electricity displaces as we go through the energy transition. Typically, a unit of electricity now coming onto the energy system in the UK would displace gas in power generation. It would displace 2 units of fossil fuels. As we go through the energy transition and electricity is used, say, in heat pumps to displace fossil fuels in heating buildings, then each unit of renewable electricity displaces 3 units of fossil fuels. And as we move into electric vehicles, away from internal combustion engines, then each unit of renewable electricity displaces 4 units of fossil fuels. So it's a myth and a fiction to think that we need the same amount of renewable energy as the fossil fuels it's displacing. We need very significantly less And that's very fortunate for us, because if that weren't the case, the energy transition would indeed be very difficult. So let me say a bit about energy efficiency, often the neglected part, I think, of the energy transition, but hopefully I've begun to show you why it does matter. And actually, energy efficiency has always been important for emissions reduction. This diagram is taken from an International Energy Agency publication. The blue bars there are the global emissions from the energy system in the years 2000, 2010, and 2020. And then the other coloured bars show you how we've got from 2000 to 2010 to 2020 with the four drivers. There are only four things that can, in aggregate, that can affect overall emissions. They are population, GDP per capita, the energy intensity of that GDP, and the carbon intensity of the energy. They're the so-called components of the Kaya identity. And you can see, unsurprisingly, that population and GDP growth tend to push emissions up. The only significant countervailing factor in the last 2 decades has been energy intensity reduction, i.e. energy efficiency improvement. There have been some changes in carbon intensity, relatively small, and actually in the wrong direction in the first decade of this millennium. Getting better in the second decade, and I think as we move into the renewables transition, will be even better in successive decades. But energy efficiency has always been an important part of emissions reduction ever since the earliest climate change agreements. We think that will go on being the case because the potential for future demand side reductions remains large. We haven't actually run out of energy efficiency opportunities. Indeed, as I've shown you, the energy transition itself creates more scope for energy efficiency improvement. The IPCC split its assessment of the scope for energy efficiency improvement, demand side improvement, into 3 areas. The blue, socio-cultural factors, what some people might call behavior change, relatively modest in most cases. Much more significant, the changes in end-use technology, largely dependent on the factors that I've been talking about earlier. But also what the IPCC call infrastructure change, and I think that is worth a bit of attention to, given the significant scope that it has. And the overall message then is that the reason that energy efficiency can play such a large role is that there are 3 components to energy efficiency improvement as we move through the energy transition. There's what you might think of as traditional energy efficiency measures: insulation, heat recovery, better process control, some behavioral and management measures as well. There's the new efficiency options enabled by electrification that I've been talking about, particularly electric vehicles and heat pumps. But then there's the broader systems, broader changes in systems in which energy is used. So these are forms of energy efficiency that are often forgotten, but are really potentially very important. So obvious examples in mobility: shifting from cars to public transport or cycling. The individual piece of technology isn't more efficient, but the mode is more efficient. If we want to improve industrial energy efficiency, we can also think about the circular economy, using recycled materials rather than making new energy-intensive virgin materials. And of course, in the food system, a shift to more local, less processed and plant-based diets is also a form of energy efficiency. When you take all those into account, and we did this in a major study in the UK 3 years ago, the conclusion we reached is that a typical developed economy can halve its energy use whilst continuing with economic growth and improved welfare. And that very large change is because you have opportunities in all 3 of those opportunities. That has really potentially quite important implications globally. So this is another diagram from which my colleague Radhika Kozla pointed me towards, showing global energy use in each of the major regions of the world. Again, these are per capita energy use, and you can see that Europe sits there towards the middle, above global average per capita use, but not as high as the Middle East, the former Soviet Union, and North America. And what we're saying is that reliable studies now show that that European number could be halved. So that means that European per capita energy use could fall to below the current average. In other words, everybody in the world could live at current Western European lifestyles, whilst the world uses less energy than it uses today. And that's, I think, a dramatic conclusion. We don't actually need huge amounts more energy to bring to good living standards the people in Africa and South Asia who are living currently on subsistence energy levels. In short, if European energy use can be halved per capita, then global energy demand can be decreased with everybody reaching European living standards. So my conclusions for energy demand are really that energy efficiency will make a major contribution to energy system decarbonisation. Indeed, zero carbon energy will not be able to decarbonise the global economy quickly without efficiency improvements. Efficiency is often a cheaper option and has multiple other benefits. And the constraints are often political, social and organisational rather than economic. So what are the remaining challenges? I'm going to run through these quite quickly given time because I want to allow time for questions. And I'm really going to focus on two. The first is the challenge of variability. These two diagrams show you the pattern of electricity use in Germany in a week in May, in first 2012 and second in 2020. You can, with solar is yellow and wind is blue. The other fuels are brown or grey, depending on the diagram. And you can see that by 2020, you've got these huge intrusions of solar energy in the day and much more wind energy, meaning that rather than solar and wind topping up the energy system, they are dramatically changing the pattern of energy use. And if we double and treble, and those are the German goals, that the role of solar and wind, you can see there are large portions of time when fossil fuels are not making a contribution and when renewables are actually providing more electricity than the system needs. So there's a huge challenge in this variability, and we need to think about sources of flexibility in the electricity system in order to accommodate that. There are multiple ways we can do that. We can look at this as a diagram taken from some work in the Oxford Martin School Integrate project a decade ago now, when we first looked at these challenges. And you can see, and our conclusion was that flexible generation, storage, interconnection, demand side response, i.e. flexible demand, can all play a contribution, but that delivering them can be complex. I think people tend to focus on storage, probably the biggest source of flexibility in the system. And of course, in the short term, for short-term storage, batteries will be important. I'm not going to say a lot about battery technology today because my Zero Institute colleague Paul Shearing is going to be talking about batteries later in this seminar series. But suffice to say, they are probably a game-changing technology for diurnal storage. We also need to think about longer-term storage, and this is a diagram taken from a Royal Society publication led by Chris Llewellyn-Smith, also of this university, making critically the point that we will need to deal with long-term variability, particularly on systems with large amounts of wind power. We get low wind periods for of order a week quite frequently. Hydrogen in salt caverns looks to be the most feasible option. It is relatively inefficient. It will add 20 to 30% to the cost of electricity. But all the calculations indicate that 100% renewable supply systems are still going to be the lowest cost and certainly significantly cheaper than gas-fired power in Europe at the moment. The second challenge we need to think about is the so-called hard to decarbonise sectors. And if we'd been here 15 years ago, people would have had the list of sectors that you can see there as saying, well, these are going to be hard to decarbonise, difficult. Particularly difficult to electrify. And in all these cases, there certainly are challenges. But I think thinking is changing as people come to terms with the fact that we do need to decarbonise these sectors. So the traditional thinking there in the middle column would have been, well, yes, we can use electricity for lighting appliances and cooling. But if we want to look at any of the other areas, we're going to need to think about some other sort of fuel, something we can burn, whether it's biomass or hydrogen. I think now that the current thinking has changed. Most people think that electricity will predominate in decarbonising heating, in decarbonising vehicles, perhaps also in decarbonising industrial heating, and perhaps also in marine and aviation short haul. It does leave some areas where hydrogen or biomass is likely to be required, making ammonia, making steel, long distance aviation being the obvious remaining challenges. And there, I think hydrogen is in most cases most likely to be the viable option, but certainly not every challenge has been solved. So just end with my key messages, really. We can't stabilise the climate without huge reductions in fossil fuel use. That's very clear. And we can't get huge reductions in fossil fuel use without a radically different energy system. So we need a radically different energy system. Renewable energy, electrification, and improved efficiency look like the central elements of the solution. And really importantly, they've got major synergies. They certainly need investment. They are, in many cases now, getting much more investment, but there are still some challenges to address. Despite the challenges, I'm pretty confident we can get to a zero carbon energy system sometime this century, maybe not by 2050, but we should be a long way along the route by then. I'll end it there, and we will look at some of the questions that have been coming in. Give me a moment while I look at the Q&A, which I now have in front of me. So the first question is from Pratchett. Within heat and work renewable energy systems, can just transitions be infused pervasively to allow carbon neutrality, as decarbonisation is a big ask given the evolving landscape of development as well as emissions? Yeah, obviously right. And the important point there is that without justice in transitions, we're unlikely to get a transition. And the most extreme cases of that, obviously, are people who don't have access to electricity or other forms of modern energy in sub-Saharan Africa and South Asia at the moment. I think the good news there is that in those environments, solar PV is the cheapest technology. We no longer need to think about building giant coal-fired power stations and transmission lines to get electricity to rural areas. The technology from smaller scale PV with batteries should be there. Delivering it is clearly a big political ask, and it's pretty clear from what's happening in the UNFCCC that negotiations that The global north isn't giving enough support for those transitions in the global south. So whether it happens or not, I think, is a political question rather than a technological question. I'm rather optimistic about the technological potential. If I just go on down, the next question is from Don Wyard. Do you have a view on the optimum generation technology for the mix of intermittent renewables versus firm dispatchable low carbon sources to deliver the most cost-effective outcome at the whole system level? Solar and wind may be cost competitive versus nuclear at an individual level, but many of those calculations do not account for other system costs. So yeah, this is certainly right, Dom, that we need to think about the whole system costs. The Royal Society, and the answer to the question, I think, will depend on the country that we're in. If you're in the tropics, where you've got a good solar supply and relatively limited seasonal variation, then the main challenge is diurnal storage, and batteries look like a good answer. So solar battery systems will be good. At the latitude that I'm sitting at, where solar is not so as useful, it's still very useful, but not as useful because its supply in winter is not so strong, and we are on a winter peaked energy system. Then that's where I think wind will be more important. Wind, as I mentioned, has got these longer duration gaps, which mean we need longer duration storage. The Royal Society study led by Chris Llewellyn-Smith that I mentioned looked at this in some detail for the UK, which is probably reasonably typical of countries at latitude 50 to 60. And it concluded that a 100% renewables electricity system was a better option than one with so-called baseload generator like nuclear on it. And that's largely because nuclear is currently hugely more expensive than other forms of generation. 3-4 times the cost of wind and solar in the UK. How am I doing?
Right. There might be one or two that have been upvoted.
Okay. Could you read out the ones that have been upvoted then, please, Helen?
Yes. Let's see. So this one has 4 upvotes. Have you talked about the private sector?
No.
Okay. What do you see as the role of the private sector in driving energy efficiency forwards? Is this likely to be primarily investment in or development of innovative renewable generation or heat recovery or EV projects?
Well, the easy answer is yes, all the above. The nature of energy demand and energy efficiency is that it is diverse, it is highly distributed geographically, but perhaps more importantly, it's distributed across all those different energy services that I set out. So we need each one of those to be delivered as efficiently as possible. The key technologies, I think, are going to be in transportation, going to be electrification, in buildings, heat pumps. Difficult to find a single one in the industry sector because, of course, industry is making such a wide range of different products. But also, don't forget those broader systemic changes in the sectors that use energy. There's the circular economy, the shift to sustainable mobility, and the changes in diets as well. Now, all those also make a big contribution to improved energy efficiency, and they are in most countries they are dominated by the private sector. It's the private sector that's supplying those services and supplying the capital equipment to convert energy in those sectors. So the private sector has a huge role, but of course that doesn't mean we don't need policy input as well in order to ensure that the incentives for the private sector are there to make the low carbon decisions.
Can I read another couple that have
Yep.
been uploaded? So this one says renewable energy infrastructure tends to have a short lifespan and use non-recyclable or hard to recycle materials like carbon fiber. Please can you comment on how to make this more circular?
Yeah, it's a good question. And of course, you can think that in an ideal world, we'd want to decarbonize steel and cement, which are the big carbon intensive inputs into renewable technologies. We want to decarbonize those before we set about using them in large amounts. Unfortunately, there's a chicken and egg problem there, isn't there? That you have to cut into the system somewhere, and I think the place we can cut into it fastest is in electricity. Is shifting towards low carbon electricity generation, and then using that low carbon electricity to decarbonize the rest of the energy system. That's certainly the way that we're going to decarbonize steel production, for example, partly by shifting to a more circular economy and therefore using electric arc steel furnaces. But to some extent, we're still going to have to make new steel, green steel, and that's probably going to involve a shift from traditional coal-based manufacturing to hydrogen manufacturing, and that again will probably be green hydrogen, i.e. hydrogen made from electricity. So it would be nice if we could make wind turbines from green steel now, but in practice we're going to have to make a lot more wind turbines before we can make a lot of green hydrogen in order to make green steel. I think we start from electricity and the energy efficiency options that are currently available.
And there's one more with a number of upvotes. So this one says, could the world truly live to European standard? Is European energy use not skewed by the fact that goods produced by heavy industry are imported? And then, so he says the thrust of this comment is not that global inequality is at all acceptable, just mindful that Europe is cheating in its decarbonization due to carbon leakage, etc.
Yeah, it's a good point, Jack, and certainly the energy statistics that I've shown and used, because they're the ones that are commonly used, are what are called production based. So they look at where energy is used and carbon is emitted, rather than consumption based, i.e. looking at where the products are used. And you certainly get a slightly different picture if you use consumption-based statistics, but we shouldn't exaggerate the overall change. I mean, firstly, of course, Europe does produce a lot of its own goods and services. Secondly, these arguments are true in industry, but they're hardly true at all in buildings and transportation, because the energy is used where the service is provided. So it's true. It alters the picture for industry, which is 30 to 40% of global emissions and energy use. So it certainly makes decarbonisation a bit on a consumption basis a bit harder in OECD countries and a bit easier in the big exporting countries such as China. But of course, globally, it doesn't affect the overall decarbonisation challenge, because the one thing we know is we don't have much trade between the world and any other planet. So yeah, you could say European living standards would be a bit lower if we didn't have access to cheap imports from particularly East Asia. But I don't think it changes the big picture. It just means we do need to be a bit cautious about the exact numbers. Helen, any more upvoted?
Yes. So Here's one. Are the displacement ratios purely based on energy content? If we consider infrastructure, availability of solar and or wind, how would the implementable displacement ratios differ by country?
So I assume there that you're talking about the numbers I gave of renewable electricity substituting for 2, 3, or 4 units of fossil fuels, depending on what it's substituting for. If you take into account the embedded energy and carbon emissions in the renewables technologies themselves, it makes some difference, but again, not a big one. So a typical wind farm has a wind investment has an energy payback period of less than a year, i.e., after it's been operating for a year, it's already paid back the energy that went into making it. And common sense tells you that it can't be a very long time period. Otherwise, these technologies could never be cost effective, and certainly not as cost effective as they are. So it affects the results a little bit, but not. It doesn't change that broad picture that we can displace very large amounts of energy, and we can use energy much more efficiently by shifting towards electric technologies.
So there's another one with a few votes. From an energy systems perspective, which sector or industry in your view is currently the biggest challenge for achieving net zero?
Yeah, that's a good question. So if we start from the easiest ones, I think it's pretty clear that anything that's currently and historically been an electricity use is relatively easy to decarbonize. I think the three that I would that we're there's then a range of technologies like heating not very well insulated buildings, heavy goods vehicles that are we sort of know how to decarbonize them. They're not as easy, but it can be done. And then there's some areas, cement production, long haul aviation will be the two that spring to mind, where if we're truthful, we don't know how we're going to decarbonize them. That doesn't mean there aren't any options. We can think of technical options for doing it, but are they demonstrated commercially at the moment? No, they're not. And anything that isn't commercially demonstrated at the moment, it's quite difficult to see that it will be universally deployed by 2050. That's why 2050 is decarbonisation is such a tough target.
Can we go for one more?
Yeah, happy to go for one more.
Okay. So to what extent, this is a two-part question, to what extent and how quickly does all this happen on its own versus needing a policy push or specific effort to decarbonize, rather than simply seeking a more efficient and less expensive energy system? And then someone else has said, or the flip side, how much can policy or politics act as a barrier to this happening? And how much can the public sector change the economics of it?
Right. So it's a good question, and obviously it has rather different answers in different political contexts. We have certainly needed public policy intervention to get where we are on the technologies that are now coming through in large amounts. We would not have wind energy where it is now if it hadn't been for Danish public policy in the 1970s and 80s, which was set up after the 1970s oil crises. We certainly wouldn't have solar at the cost it is now without German feed-in tariffs and Chinese government decisions to invest hugely in solar production. So public policy is clearly very important at that point in the innovation chain. And we won't get a shift to electric vehicles and heat pumps without appropriate public policy, because at the moment they are still slightly, in most places, more expensive options than the fossil fuel options. On the other hand, I think once you reach a certain point, and I think we probably are now largely there with wind and solar, good public policy can help. We are, I think, about to see an experiment in the United States of America as to how far disastrous public policy can stop wind and solar. It would be interesting to revisit that question in 4 years' time, by which time I hope we'll have a more sensible government in that country. But I'm relatively hopeful. Wind in particular in some of the Midwestern states and solar in the southwest of the US are so much cheaper, so much better options than fossil fuels that we are seeing them being deployed. So I think we are seeing we will see an interesting conflict between economic reality and the I can't really find a polite way of describing the current public policy there. There is no way of politely describing it. So short answer, yes, we need good public policy in some cases. In other cases, the market might do it on its own, but public policy is certainly going to help it along.
I think that pretty much brings us to time. Any concluding remarks, Nick?
I don't think so. I'm happy to take away that. I'll just say I'm happy to take away the rest of the questions that are here, and if colleagues are going to leave this open, I'm happy to answer those in writing. Do I need to say anything about the rest of the series? So the series continues for the next 5 weeks. I'm going to allow my colleagues to say who's on next week, because I can't personally remember. Helen.
It's the engagement team. They'll be talking about, from Oxford Net Zero, they'll be talking about net zero in policy and practice.
And if you want to find details about all of the rest of the seminars, visit netzeroclimate.org.
I hope that was clear, and I think we can probably put up a slide to that effect as we close. But just to say thank you very much for joining. I hope you found it interesting, and look forward to seeing you at future events.